Welcome. We've been talking about implicit differentiation, but what does it mean? We have an equation for which we assume that there is a solution which is a differentiable function. But how do we know that? In applications, perhaps there may be other considerations which lead us to believe that this equation has a solution which is a differentiable function, but even that is not always certain. I will use this example, which we did last time, to illustrate a special case of the implicit function theorem, which is what we need in the one variable case to figure out what implicit differentiation really does. So in this example, we had an equation 4xy equals x squared plus y squared quantity squared, and we found its derivative at the derivative of y with respect to x when x is 1 and y is 1. And that led us to the tangent to this curve at the point 1, 1. The tangent as equation y minus 1 equals negative 1 times x minus 1, or in slope-intercept form y equals negative x plus 2. If I draw the graph of this equation and the tangent line that we got, this is what we will get. The graph of that equation 4xy equals x squared plus y squared quantity squared is this figure 8 curve, and this is the graph of the straight line which we decided was the tangent. Of course, the straight line does look like a tangent to the graph at the point 1, 1, which is here. What does it mean? Because graph is obviously not the graph of a function. The whole graph is not the graph of a function. But if we take a small portion of the graph around the point 1, 1, it is the graph of a function. That's the point of implicit function theorem. It says that suppose you start with an equation and carry out implicit differentiation. One thing that can go wrong, which we haven't seen in any of the examples we did, is that all the y prime terms cancel out when you try to find the derivative at that particular point, so you cannot solve for y prime. If that doesn't happen, so that you have a number times y prime equals another number and y prime equals a regular number because its coefficient is not 0, then there will be a small segment of the graph of the whole equation around the given point, which is the graph of a function. So in this particular case, if I take a small portion of the graph, there's clearly the graph of a function. That function will be differentiable at that point, and its derivative is what we calculate using the process of implicit differentiation. This is really what implicit differentiation accomplishes.